So my name is Leonardo Cardoso. I'm from France, here with my colleague Amaury Paris. I am an associate professor at INSA Lyon, and also a member of the INRIA team, as is Amaury Paris. We'll be talking today about this testbed that we have back in Lyon. It was created for wireless research, but as I will hopefully show you and try to pick your interest, you can use it for many other things. And we're also going to talk about a framework that was designed within our team by Amaury that enables researchers who are interested in doing research on IoT systems to use and then to try to maybe develop new schemes for transmissions for these kinds of systems. So let me start with a bit of a context so you understand better where these things are coming from. So we're talking about IoT systems here, and as we know, there are more and more IoT systems being deployed in the world, and we are expecting like many systems, many sensors, devices transmitting all of the time. Sorry, and that is actually a big problem because we have these sensors which are essentially transmitting very few data, but since there are a lot of them, this will create a big problem with respect to the traffic. Right, so as we know, as we are expecting actually, usual ways to accommodate this kind of traffic is getting less and less effective for these networks. So we need to come up with new systems or new technologies that enable the communication of many devices. It's in the order of billions of devices all at once in the same area. So the biggest problem is that if you have all these systems transmitting, they will have lots of collisions and interference in general, and then this will create problems with respect to latency, to energy consumption, and to battery lifetime of these devices. And as we know, many of them are actually using batteries to operate. So the researchers, they are actually interested in trying to understand new techniques or find new techniques to enable the communications of these systems. And what they usually do is that they will start with theory. So they will start developing theoretical and mathematical systems and technologies. And then after that, they will go on to simulations to try to see if their techniques are good enough for what we are expecting. And we think that if we want to, for example, to develop new kinds of techniques which are non-orthogonal, it would be better to really try them with real transmissions, because that will enable the researchers to capture the fine effects of the RF systems, but also of these systems transmitting all at once, which is not something which is easily captured in simulations. So that's why we came up with S3CAP, which is a framework which runs on CorteXlab, but not only, as you will see later, and it allows researchers to actually try out new techniques with real transmissions. What is the kind of thing that we can do with S3CAP? So we can create new channel access policies. So we can try to understand how many systems accessing the medium all at once, how that will behave. But we can also work with new systems for the transmitters and for the receivers to try to, for example, to understand how the interference works, but also new systems of communications which are non-orthogonal. So I will now just tell you what we're going to present. So this was just the context. Right now I'm going to talk about FIT CorteXlab, which is the testbed that we have back in Lyon. Hopefully that will spark a little bit of interest in some of you, and then you'll be able to maybe come and use it. And then I will let Amaury speak, and he will talk a little bit about the framework and about its usage. All right, so let's start with the FIT CorteXlab testbed. So Maybe we should start with the name, FIT CorteXlab. FIT stands for Future Internet of Things, and CorteXlab for Cognitive Radio Testbed and Experimentation Lab. This is roughly a 180 square meter room, which is based in Lyon, France, and it's shielded, and it is completely isolated from the outside world. So we have 60 dB of isolation with respect to the whole frequency range that we're able to use in this room, which is quite interesting, meaning that we can do experiments in any frequency bands inside of this range without disturbing what's happening outside of the room. So we have 40 SDRs. They are disposed inside of the room, and as you will see later, I have a map of that, among USRPs and Pico SDRs. All of them is GNU Radio compatible, so for the people who are doing GNU Radio schemes, then you can come, bring them over and test them there. So one thing which is very important for the scientific community is reproducibility, right? So one good thing, well, actually one problem of doing experiments is that if you do experiments today and if you do it tomorrow, then sometimes you cannot compare the results because something might have happened, right? Maybe you have some interference, or maybe the channel changed. So the good thing about using a room like this one is that you can actually guarantee that your propagation environment is exactly the same and that you will not have interference. So the experiments, they will run in computer nodes which are connected to an SDR device. And the whole idea here is that our system will deploy your code automatically within a Docker container in these computer nodes, and that this will run, and then, so everything is done, so the system controls the whole thing, so you don't have to do anything by yourself. Then, of course, we have other kinds of equipments. For example, we have octoclocks, which allow you to use, if you wish, which allow you to synchronize all of the nodes. We also have a big server with GPU, so for people who are very interested with deep learning, then you can also do that with us. And we have robots in the room for those who are interested in doing mobile kinds of experiments. Most importantly, the room is free to use, so you just need to access our site and ask for an account. The link is right there. And then you will also find some tutorials and some other resources that you can use to start working with CorteXlab. This is what the room looks like. So each one of these crosses is a node antenna, and that's roughly the spacing between two antennas is 1.80 meters, and you'll have all these different kinds of nodes which are distributed inside of the room in that way. And this is what it looks like from the inside. So you have the robots. This is the first thing you see. The nodes are attached to the ceiling, so you see some computers, some antennas, and then also some SDR cards. So I would just like to talk a little bit about some things that you can do with CorteXlab. So of course, research is one of the most important ones. This is what we created the room for. If you're doing research and you need to test schemes or techniques within a large number of nodes, and you don't want to do that by yourself, like going to each one of the computers and starting and stopping, then you can do it with CorteXlab. Also, teaching. I myself have been teaching with CorteXlab, and it's very useful, especially during the pandemic, where you can have the students access the room remotely during the confinement. For those of you who are actually trying to learn how to use GNU Radio or how to use these radio cards, you can also use them inside of the room. So you cannot do it directly, but you can create your own flow graphs with GNU Radio and then port them and then put them onto CorteXlab to test them out. One usage which is very interesting, but we haven't done it yet, is to automate tests. So if you have, for example, your own systems that you want to, your own creations that you want to test over and over, for example, if you change something and then you want to retest it, then you can do it in an automated fashion in CorteXlab, but not just for the code, but also for the connection with the radio cards and the transmissions themselves. And of course, it's open to any other usage that you may think of. So right now I'll let Amaury speak to you about the S3CAP framework.
Thank you, Leo. So now about the S3CAP framework. So I'm going to start by presenting what it can do. And in the second part, I will try to present, so because I'm just getting started with GNU Radio, so evidently quickly I came around a few issues when trying to develop this. So I'm going to try to present what the issue was and what kind of solution I've tried to implement. So if you have any income on this, I'm very happy to hear about it. So the framework was actually built to work on, like Leo said, on uplink channel access. So the way we've seen it is that we can work on either the access policy, deciding when we're going to transmit something on a shared channel, and the second way was robust coding, so having a signal, a physical signal, which is going to be more resistant to, for example, interference. So the system is based like a star system, so we have the base station in the middle, and all around it a bunch of nodes. The wireless uplink channel from the sensor to the base station is a time frame, and you have a number of slots in it. And on top of that, we have a wired control channel. So this one is uplink and downlink. It's error-free, and it's based on ZMQ message passing between all the nodes. So if we have a look at the shared timetable, it basically looks like this. So each frame starts with the processing part, in which we apply the access policy. So the access policy is yours to implement. So you're basically going to write a bunch of lines of code to say, based on this condition, I'm going to send something in the first slot or in the second slot, or not. Yeah, you don't want to send anything. So the access policy is here to apply the access policy you've implemented and then prepare the code. So the complex samples, which are going to be sent later on, are actually prepared in here to avoid delay during the transmission period. So the access policy. Then starts the control period, because we have a lot of, it's a slotted transmission, so we have to make sure that the transmission and the reception is well synchronized. So we have a synchronization algorithm, which I will come back to later. We have to have a small time period to send and exchange control messages, the one I mentioned earlier with the wired control channel. And finally, we have the transmission period, in which all sensors will transmit or not. And eventually, if there might be some collision if they transmit all at the same time. So this is the end of the first frame. And after that, we have the second frame starting, which will start with the post-processing part. In this part, we will gather all available information we can find, like error, received messages, control messages, and so on. This information will create a feedback which will be sent to the access policy. It will use this as an input to decide, should I transmit in the next frame? In which slot should I not transmit? Why should I transmit? What should I transmit, sorry? And so on, and so on. So, this might come as a surprise to you, but not everybody knows GNU Radio and masters it, and especially people working on the Mac layer, people who want to work on the access policy part, and for them working inside GNU Radio, implementing complicated Mac layer inside GNU Radio can be time consuming. So it was in our interest, at least for the people we wanted to work with, to actually have this access policy being implemented outside the GNU Radio environment. So here we have a simple access policy connected to receiving feedbacks from every sensor on the base station. So it's a centralized access policy. We can also have this decentralized, so each sensor has its own access policy that only knows the feedback it's giving it. This uses a simple API we've developed. I will show it later on. This had a second interest for us, is that because we are also working with machine learning, so we have, Leo mentioned it, we have a server with a lot of GPU card on it. So this was actually very helpful for us because we were able then to put the access policy on the GPU server and sending back instruction on the server, which were actually controlling the USRP. So if we have a quick, distributed implementation for what I just said. And so if we have a look at the access policy for one node, here, so sorry for putting code in my slide. So here behind the receive and send instruction function, we have just a simple ZMQ socket, which enables communication from and to GNU Radio to receive the feedbacks and send back the instruction I mentioned earlier. And we're just going to deal with this with the PMT dictionary object. So we put all the feedback and the instruction in this object and send it. Here we just have a simple condition. We check the received control messages, and based on that, we decide to transmit or not on here the first slot. Once we have prepared this instruction, it's being sent to GNU Radio, and this is the access control block, so it's a block we've developed. He will receive the instruction and decode it and extract the content of the message we want to send, so the payload, and he will send it to the physical layer here. The physical layer will prepare the complex samples, and those samples will be stored in the sensor scheduler. So all of this is happening, if you remember, in the processing period of time. What's interesting here is that the physical layer, here it's LoRa, you can take it out and put it as a physical layer of your choice. So if you have a physical layer, or I don't know, blocks to create your own signal, you can just take the LoRa one out and put yours in, and this way you can enjoy all the slotted and simultaneous transmission that our framework offers, but with your signal. So yeah, the physical layer will generate some complex sample. It will be sent into the sensor scheduler, and this one will store it inside his buffer. So all of this happen in the access policy part here, and then we have the transmission here in the transmission part. So before that, we have to make sure that everything is well synchronized. So this is what I will present now. In the layout of our system, we have an octoclock, which Leo mentioned just earlier. It provides the PPS signals for clock synchronization and a 10 megahertz signal for sampling synchronization. We also have our sensor and the base station. And here, at the bottom here, every time period in the frame can be set with a time length, and the base station will compute the number of samples it matches the time length we've set for each period. So here is just a sample count to make sure that we respect the time length we've set at the beginning of the flow graph. So when we start running the flow graph, we use the octoclock to synchronize internal clock of each sensor and the base station using the PPS signal. So after that, everyone shares the same internal clock. And then the base station starts receiving some sample, so on, so on. And at some point, it arrives at the beginning of the synchronization period. And when the base station receives the first samples of the synchronization period, it's going to check the internal clock time of the USRP. And based on that information, will compute a time to send information, which it will send to the sensor. The sensor will then take all the samples, the complex samples that it has in its buffer, and send it with two tags, the TX time and length tag to the UHD, so that it can be sent on the right time. And then we receive the signal. So this was the first way we tried to implement the synchronization for our system. And obviously, after that, we tried to make some measurement to make sure what it looks like in real life. I want to give a big thanks to Cyril Morin for this, because he's the one who has done all these measurements. So I don't know if he's watching, but yeah, thanks to Cyril. So for the transmission synchronization, so we had to node transmitting at the same time, and then we look at the reception, see if the signal has any delay between the two or not. We had approximately 150 nanosecond delay, so this was enough for our requirement for the project we were working on. And after that, we looked at the reception synchronization. So we looked at the time between the beginning of the reception window and the actual time when we received the first node signal. And this was less good, I might say, because we had an average of 0.7 milliseconds. So we tried to think about it, and to the best of my understanding, at least, we think that it may come from the fact that when we arrived here, what I showed earlier, when we arrived at the beginning of the synchronization period, we check the internal USRP time, and assume this time we get is the time when we received the first synchronization sample, which is not true, because we actually, at this time, already have a bunch of other samples in the buffer. So this creates a delay, and this is what creates the error here for the reception delay. So again, with the help of Cyril, he offered a new solution where we can ask the UHD block, the UHD source, to provide the RX time tag. This will tell us for one sample exactly when we received it, and this way we have a more precise time to send information. So we haven't yet implemented it in the framework, but from what we've seen for the measurement we've tried, we should have, as you can see, a much more precise synchronization. Oh, and yeah, it's also very useful. We're also working on the generation of dataset, and this is very useful if you want to have time-labeled information when transmitting a signal from different nodes and receiving it at some point. This is very useful to have yeah, precise label. Now comes to the usage of this framework. You can run in feed CorteXlab, as Leo mentioned it, but you can also run it in your local computer. So if you just want to download the Docker image and run it, that's something you can do. It can be useful for many ways. We have so far the LoRa physical layer, which I've shown in the slides. We are also working on an NB IoT physical layer, homemade. We still have a few issues. It's working when we run it in local, but not in CorteXlab, so we're still working on that. And yeah, if you want to use the framework, it can work with your physical layer or any signal you might want to use on this framework. And last point, it's possible to emulate nodes in the feed CorteXlab testbed. So we have like 40 nodes, something like that. And if you want to make a test with more nodes than that, you can just emulate them in one server, one USRP, and add the signal, and then you have simulated nodes. We have a tutorial on the way. I still have to find time to write it. It will be a really dummy example with two nodes randomly transmitting on one shared channel. And it would be a good way for you to understand how the framework works, and how you can modify and implement your access policy, modify the physical layer, and use the synchronization algorithm. So it will be at this web page. For current and future work, we're going to work, like I said, on the NB IoT physical layer. We would like to try to implement a reinforcement learning access policy based or made for LoRa. And we actually had some coworkers of ours working on the study of statistic in interference, like baseband IQ sample during what happened during a collision. And yeah, that's it for me. Thank you very much for your attention, and thank you for you guys for organizing this conference.
Can I give just a couple of words before the questions? I just want to take, since we have a little bit of time, myself and some other people back in France, we are the ones who are organizing the European Green Radio Days. And so we haven't yet found the details about this year's event, but I would just like to, tell people who are here and possibly who are watching, who are from Europe, to try to stay tuned first to find information about the actual dates and everything, and then also participate, please, because it's actually, especially during the pandemic, it has been quite hard to gather interest. And since we're coming out of that, I would like to really reinforce that. Thank you. We're now open to the questions.
Okay. Are there any questions? I saw the gentleman in the back.
Yeah. Okay. Have you looked at anything besides a star topology, like a linear?
Sorry?
Star topology.
You guys have a star network defined as for all your IoT?
Maybe I can answer that one. So actually the idea of the framework is to have a kind of a wide range network, like LoRaWAN, something like that. And we're trying to understand how one base station or access point can actually respond to this amount of accesses all at once. So this more or less restricts the kind of topologies that we can have. So we haven't tried other topologies because of that. Actually, this framework is coming from a project. So we had a project, a French project, a research project, and within this project, we wanted to try to understand what happens when we have interference and all these things. And instead of like making one big simulation or one big experiment, we decided to make that into a framework that people could use. So this is where it comes from, if you need a little bit.
I get that. Mine is that we've had several initiatives here, like especially in the transportation, like rails and tunnels and bridges, where we have to have this IoT, but we can't do it in a star manner. And I'm just wondering if your framework could be expanded to how you would hook. I'm not saying it's a bad framework. Don't get me wrong. I'm just saying, can that framework be expanded to be in a more linear model than a star model?
It could probably be. I don't know if in your case what you actually mean is that there's a device-to-device communications, and then they're like trying to transmit their messages one to the other, and then passing the message on. Okay, yeah. Okay, I see what you mean. Well, right now we don't have that. We don't yet, but I'm sure if you stay tuned to our website, and if we do it, you'll be the first one to know.
Cool. Any other questions? Can someone look whether there's something online, actually? Martin has a question.
Yeah, this was a cool presentation and a lot of cool stuff. I did not quite understand that synchronization issue you talked about. You were saying like, the TX side looks good and the RX side it does not. Can you just maybe pull the slide up again? There was like a, what is it, 700 microseconds or something?
Yeah, that's the one.
Between what and what is it, like, what does this number mean? Can you just,
Which number?
the 0.7 milliseconds.
Oh, the 0.7 millisecond?
Yeah.
Yeah, so if we go back here, so we have a reception window here on the base station side, and then we try to send signal at the beginning of this reception window from the sensor point of view. So what we measured was on the base station side, how much time we had between the beginning of the reception window and when we actually received the signal here. And this was way much bigger than we expected. And so, yeah, I don't know if you want me to come back on why, but yeah, that was this number is showing off.
Yeah, it was, and I guess we could debug it now, but that's not the right
Yeah, well,
venue.
I'm happy to discuss it. Yeah.
Yeah, thanks.
Actually, the whole idea is that if we want to really test these signals interfering with each other, then we need them to be as synchronized as possible. And we were having a hard time to get that running. So that's it.
Okay, cool. I don't see any other questions online. Are there questions in the room? If that's not the case, let's give the speakers another round of applause, please.